exam, previously we were talking about mixes. And while we were doing that discussion, we said that mixes are of two types. There was one category in which we were considering mixes to be non-reacting type of mixes. That was the discussion which we were doing from the chapter number 13 of the book written by Yunus Angel. Now, this new chapter which we are going to start today, this chapter is having discussion on the second type of the mixes. The mixes in which the forming components they are going to react with one another chemically. So these mixes are called as reactive type of mixes. So the discussion is available to us in the form in the reference book, which is the book written by Yunus Angel, and the relevant piece of information is available to us in chapter number 15. Chapter number 15 of the book is having the title with the name of Chemical Reactions, and we are going to do this. We are going to follow this discussion for the purpose of a combustion process. All of us are well familiar that there are many components, there are many systems in which we are making use of the thermal energy. One quite familiar component which is basically making use of the thermal energy for the production of mechanical energy is the device which is called as heat engine. Heat engine is basically the device which basically make use of the thermal energy and converts that thermal energy into the mechanical energy, and then we are going to make use of that mechanical energy either for the purpose of traveling or for the purpose of power generation. So in this chapter, what we are going to do, we are going to discuss basics of the combustion. We are going to discuss what is meant by complete combustion, when combustion is considered to be incomplete combustion, what do we mean by the term theoretical combustion, what do we mean by the term actual combustion process. We are going to learn how to balance a chemical reaction equation, which is basically describing the combustion process. Then later on, we are going to do the estimates that how much heat we are going to expect when we are going to burn some defined amount of any given fuel. And then the last part of this chapter would be giving us this information, okay, how to estimate the flame temperature. Specifically, there is one peak temperature level which we may achieve if a combustion process which is named as adiabatic flame temperature process. So we are going to learn what do we mean by the term fuel, what is the oxidation process for the purpose of the fuel, how to balance the chemical reaction equations which are describing the combustion process. We are going to learn how to estimate the amount of the thermal energy which fuel is going to liberate during the combustion process, and we are going to estimate the adiabatic flame temperature. Fuel is basically any such component which is going to liberate quite a large amount of thermal energy while we are going to oxidize it. Conventionally, carbon, hydrogen, and sulfur they are basically the compounds which are going to give us a huge amount of thermal energy while we are going to oxidize them. This is the very first table which is available in chapter number 15. This table is basically giving us this information, how much is the energy content which we are going to get if we are doing the combustion process by using different fuels. So the first column is having this information on the variety of the fuel elements. The second column is giving us this information how much energy we are going to get if we are going to burn 1 liter of all of these fuels which are listed in the first column. The third column is giving us this information that how much quantity of a certain fuel would be needed to get the same energy which was there in 1 liter of gasoline or petrol. For example, we need only 0.89 liters of heavy duty diesel to get the same energy which was there in 1 liter of gasoline. So, for the purpose of combustion, we said that we need a fuel element, and then we need to oxidize that fuel. But fuel elements, they are not supposed to catch fire only in the presence of oxygen. For the purpose of combustion, we need to fulfill three conditions. We need supply of fuel, we need supply of oxygen, we need to brought a supply of oxygen and the fuel at certain temperature levels. For just as an example, we are having coal, and if that coal is placed in the ambient environment, that coal is not going to catch fire automatically. In order to start combustion process for that coal, what we need to do, we need to brought coal at certain level of temperature. Over here, we are having this information. This temperature is technically given the name as the ignition temperature, and the minimum ignition temperature for the purpose of gasoline is 260. Petrol is for 260 degrees Celsius. Same is 400 degrees Celsius for carbon, 580 degrees Celsius for hydrogen, 610 degrees Celsius for carbon monoxide, and so on. So we need a supply of fuel, we need supply of oxygen, we need to brought up fuel and oxygen source at certain temperature levels so that the combustion process is going to initiate. For the purpose of combustion, normally in majority of the practical applications, we are going to consider that we are getting oxygen from air. Air is composed of very many different components. Air is having oxygen in it, air is having nitrogen in it, air is having carbon dioxide in it, air is having carbon monoxide in it, air is having different other components in it. But when we are doing the analysis from the combustion point of view, we are going to consider air is composed of two components only, and those two components are oxygen and nitrogen. And we are going to consider more specifically, we are going to consider air is having 21% oxygen in it and 79% of nitrogen in it. And this composition is on molar basis. So if we are just going to take a ratio, then we are going to get this information. Every single kilomole of oxygen is having 3.76 kilomoles of nitrogen linked with it. Or in other words, we may say that if we are using oxygen from air, every single kilomole of oxygen, for every single kilomole of oxygen, we need 4.76 kilomoles of air. So once again, every single kilomole of oxygen which is there in the air is associated with 3.76 kilomoles of nitrogen, and every single kilomole of oxygen which we are getting from air, we need 4.76 kilomoles of air to get 1 kilomole of oxygen from the air. Combustion is a chemical reaction process, and mathematically, we are going to do from the analysis point of view, we are going to write different chemical reaction equations to get information about the combustion process. So chemical reaction equations, they are having some reactants in it, and those reactants, they are going to react with one another in some chamber, and they're going to form some product gases. If we are going to relate it to our heat engines, in our heat engines, they are having one chamber which is called as combustion chamber. So in the combustion chamber, the reactants which are fuel and air, they are going to react with one another and they are going to form products of the combustion process. So now we are going to learn how we are going to analyze the combustion reaction process. We are going to write these chemical reaction equations which are describing the combustion process. And while writing these chemical reaction equations, we are going to follow, we are going to consider this thing that mass of is something which is going to stay conserved, and number of atoms of each species is something which is going to stay conserved during the combustion process. Over here, there is combustion process. There is reaction equation written for the oxidation of hydrogen. Hydrogen is oxidized with oxygen to produce water. And mass balance equation, conservation of mass is given. Information is given over there that 1 kilomole of oxygen is having 2 kilogram mass of hydrogen. 0.5 kilomoles of oxygen are having 16 kilomoles of oxygen, and 1 kilomole of water is having 18 kilomoles, 18 kilogram mass in it. So mass, overall mass is conserved. In the reactants, we were having 2 kilograms of hydrogen, 16 kilograms of oxygen. In the products, we are having 18 kilograms of water. There was 1 kilomole of hydrogen in the reactants, and in the products once again there is 1 kilomole of hydrogen. In the reactants there was 0.5 kilomoles of diatomic oxygen, and in the products once again there is 1 kilomole of monatomic oxygen. If we are going to consider it diatomic, then there is 0.5 kilomoles. So these two parameters, overall mass is going to stay conserved, and number of atoms of each components, they are going to stay conserved during a combustion reaction process. So this was the one thing. There's one technical definition, technical parameter, which is called as air-fuel ratio. This air-fuel ratio is simply the ratio between the mass of air and the mass of the fuel. So this air-fuel ratio is the parameter which is going to give us this information, how much air is needed to oxidize 1 kilogram of that fuel. So we are having this information written over here, and this example says air fuel ratio is 17. This means in order to burn 1 kilogram of fuel, 17 kilogram of air has been utilized. So air fuel ratio is 17. The inverse of air fuel ratio is called fuel air ratio. Now we are going to learn how to balance the combustion equation, how to balance a chemical equation which is basically describing the combustion process. We are having this information given to us that 1 kilomole of octane is burned with 20 kilomoles of oxygen. Assuming the product contains CO2, water, oxygen, nitrogen. Determine the mole number of each gas in the products and the air-fuel ratio for the combustion process. So in this case, we are having this information. Fuel is octane, and we are using 1 kilomole of this fuel. Then we are having this information. Oxygen is being drawn from air, and we are using 20 kilomoles of oxygen. Remember, this is 20 kilomoles of oxygen, not 20 kilomoles of air. Every single kilomole of oxygen which is coming from air requires 4.76 kilomoles supply of air. For the purpose of products, we are having this information. There is CO2, there is water, there is oxygen, there is nitrogen. But we have not been given this information, how much amount of carbon dioxide is there, how much water is there, how much oxygen is there, how much nitrogen is there. Rather, we have been asked to check how much would be, how many kilomoles of CO2 would be there, water would be there, oxygen would be there, nitrogen would be there. Lastly, we have been asked to check the air-fuel ratio. So, chemical reaction equation has been written. How we are going to write the reaction equation? We have to write reactants on one side and products on the other side. For the purpose of reactants, we are having fuel and we are having air. This notation O2 plus 3.76 N2, this gives us this idea that oxygen is drawn from air. Every single kilomole of oxygen is having 3.76 kilomoles of nitrogen with it. So we are using 20 kilomoles of oxygen, so 20 is written over there, 20 kilomoles of oxygen. Every single kilomole of oxygen is having 3.76 kilomoles of nitrogen with it. We were using 1 kilomole of the fuel, so there is nothing has been written as a leading multiplier with octane. So we are getting this idea that we are using 1 kilomole of octane. In the products, there is CO2, there is water, there is oxygen, there is nitrogen. But we are not having this information, how many kilomoles of oxygen are CO2 are there, how many kilomoles of water are there, how many kilomoles of oxygen are there, how many kilomoles of nitrogen are there. So we have given random names to the information of these kilomoles. We have assumed there are X kilomoles for CO2, Y kilomoles for water, Z kilomoles for oxygen, W kilomoles for nitrogen. Now what we are going to do, we are going to write the balance equation. So while we have written the balance equation, we have in the start we started from carbon. So we are going to start writing our reaction equations from carbon. We are going to focus on the reactant side first. In the reactants, we are having carbon in the fuel, and we are having this information. There are 8 carbon atoms which are there in the reactants. Then we are going to have a look into the products. In the products, we are having carbon in CO2, and we have assumed there are X kilomoles of CO2. So X atoms are there for the purpose of carbon. So by writing carbon balance equation, we have got this information. There would be 8 kilomoles for CO2. Then we have written balance equation for the purpose of hydrogen. Once again, we have looked into the side of reactants first. In the reactants, we are having hydrogen in the fuel. Once again, we are considering hydrogen to be monoatomic. Then there are 18 atoms of hydrogen. Then we are going to have a look into the products. And in the products, we are having hydrogen in water. So over here, this is diatomic hydrogen now. And this 18 number, this was basically the number which we have obtained when we considered hydrogen to be monoatomic. Over here it is diatomic, so if we have considered monatomic over here, we have to consider it monatomic over here as well. So if when we are going to consider it monatomic, then there would be two Y atoms of hydrogen which are there in the water. So finally, from this balance, we are going to get this information y is having a value equal to 9. So there would be 9 kilomoles of water. Similarly, we are going to write a balance equation for the purpose of oxygen. Once again, we have to be careful that if we are going to consider oxygen to be monatomic, then we have to consider it monatomic on reactants and monatomic on the side of products as well. If we are considering diatomics, then it should be considered diatomic in the side of reactants and diatomic in the side of products. Author has considered it to be monatomic, and the equation is written for monatomic oxygen. And finally, we have obtained this information that there would be 7.5 kilomoles of oxygen. Similarly, a balance equation for nitrogen has been written. So now we are having all this information: how many kilomoles of CO2 would be there, how much would be water, how much would be oxygen, how much would be nitrogen. Now we have plugged in all these numbers and have rewritten the balance equation. We were asked in the problem to get this information: how many kilomoles CO2 would be there, how many kilomoles for water, oxygen, and nitrogen. This was the first part. The second part of the problem has asked us to do the calculation for air-fuel ratio. For air-fuel ratio, what we have to do, we have to compare mass of air with mass of fuel. So mass of air with mass of fuel, and mass of any component can be checked from the product of molecular mass and kilomoles of the compound which is under consideration. So mass of air, how many kilomoles of air were there, and how much is the molecular mass for the purpose of air. So we have used 20 kilomoles, but 20 kilomoles were there for the purpose of oxygen. Every kilomole of oxygen is requiring 4.76 kilomoles of air. So 20 kilomoles of oxygen would be requiring these much kilomoles of air, and this 29 is basically the molecular mass for the purpose of air. In the fuel, we are having carbon and we are having hydrogen, so we separately determined mass of carbon and mass of hydrogen and summed them up. So after plugging in the numbers, we have obtained this information that in this case, in order to burn 1 kilogram of fuel, 24.2 kilogram air has been used. So till now, what we have discussed the basics of the combustion process. We have discussed that for the purpose of combustion, we need to fulfill three conditions. We need supply of, we need some fuel, we need some source of oxygen. We need to brought that air and fuel at certain temperature level so that fuel is going to catch fire. Then we discussed that combustion process is requiring oxidation of the fuel. Practically, for the purpose of oxidation, we are getting oxygen from somewhere, and practically we are going to consider that we are going to make use of air as a source of oxygen. While we are going to make use of air, then we are going to consider air is composed of two components only. Those two components are oxygen and nitrogen, and we have considered air is composed of 21% of oxygen, 79% of nitrogen. This gave us this number that every single kilomole of oxygen drawn from air is having 3.76 kilomoles of nitrogen with it. For 1 kilomole of oxygen from air, we need 4.7 kilomoles of air. And then we learned this thing that during a combustion process, overall mass is something which is going to stay conserved. Reactants are going to react. The bonding between the elements which is going to break new bonds, they are going to form new components, there new species they are going to be formed, but overall mass is something which is going to stay conserved, and number of atoms of each component which were there in the reactants would be the same as the number of the atoms of the similar species in the product gases. And then we have learned how we define air-fuel ratio. We have seen the process of balancing chemical reaction equation. Up till now, the calculation or the analysis which we have done so far, for that analysis, we were given this information: how much air, how much oxygen was used to ignite a given amount of the fuel, and then we were having this information what to expect in the product gases. We were given this information in the products. These would be the compounds. In the coming sessions, we would be discussing how to estimate that what species we're going to expect in the product gases. We're going to learn what do we mean by the term complete combustion process. We're going to learn what is incomplete combustion process, how an actual combustion process differs from a theoretical combustion process. Then we are going to discuss the heating values and how to estimate them. Then we are going to discuss how to estimate the adiabatic flame temperature. That's all for the today for this introductory section, and we will keep you posted with the ongoing information. Please visit your LMS accounts time to time to see the postings over there. I wish you all the best, and stay safe, stay healthy, and stay in touch. All the best. Allah Hafiz.